purpose of my talk is, we've talked about ModSim already a little bit. I'm going to go into a little bit more detail on that, and demonstrate how modeling and simulation can be united together using the 3D Experience platform, and thereby providing an end-to-end product development process, as Jonathan mentioned earlier. And we simply call this integration of modeling and simulation ModSim, as you may have already guessed. I'm going to demonstrate this through the design of a high-speed connector, which we actually needed to upgrade our smartphone reference model. The first iteration or design of the smartphone model was using lower speeds, and nowadays speeds are a lot faster. So we needed a new connector that could handle higher speeds. And again, we do this kind of work so that we have models that are relevant to the high-tech industry and help us to position workflows, the best simulation approaches and techniques that we can to our customers. So I'm also going to start with the challenges, and these are sort of general challenges in the high-tech industry. First of all, high-tech industry is particularly fast-paced, very fast innovation, and that means there's really little time to create prototypes. You really want to minimize the number of physical tests and minimize the number of design iterations. But then there's also the technical challenge of designing components that can handle super high speeds of today's signals. So for our smartphone model, we wanted to update actually all the PCBs, flex connectors, and the external connector, which is what I'm focusing on here today, and actually external cabling, to USB 3.x speeds, and that required some reworking of our design. But another major challenge is just simply the inefficiency in the development process itself. So companies traditionally have used a very manual process, I think, as has already been mentioned, which typically involves sharing files, emailing them around, and each analyst may develop different versions of the models for their own purpose. And quickly things can get out of hand. It gets very confusing. Which model are you working on? Oh, that's different to the model I'm working on. I'm sure we've all experienced that. And it gets very complex when you start making design iterations and you have to reshare models and files. And most importantly, from the analyst point of view, you have to redo all the simulation settings each time. And it's also, we tend to take, or in the past, we've tended to take a rather atomistic approach, where the design is optimized for one aspect of the physics, such as signal integrity, separately to another aspect, such as structural performance. And that's also, sort of inefficient way of going about the whole problem. And, we really want to change the way that we work, collaborate in teams, and have much more efficient workflows. So again, traditionally, the designer shares CAD data with multiple simulation engineers or analysts, and each engineer works on their own local version of the CAD to set up the physics scenario and evaluate the results. And if those results don't meet the requirements, that triggers a discussion for the design change. Emails start to be exchanged, and eventually the CAD designer will need to update the model, reshare the models back, and it gets very complicated very quickly to ensure that all stakeholders are working on the same versions of the design. And this process is very iterative, and it has to continue until the final KPIs are met from all the different multi-physics design points of view. And this kind of, manual exchange of data and communication really does slow down the whole process, and it's also prone to errors. So with the ModSim approach, we're offering a new simulation-centered enterprise approach. The CAD model is centralized, and instead of downloading data locally, each stakeholder accesses the same data. We like to sort of call it a single source of truth. Everybody's working off the same model to perform their particular simulations. And I think has already been mentioned, any change in the CAD design triggers a notification to the analysts through the platform. They're notified, and that change becomes visible automatically to all the stakeholders. And this really keeps things in sync, makes sure everybody's working off the same model. And the communication can take place via a dashboard on the platform, and all the different actions during the project can be tracked using project and change management. And through this unification, we're able to achieve full associativity between the requirements and the detailed design, complete traceability throughout the design cycle, faster optimization of the design, especially because of the integration between the multiple physics. So it really becomes simulation-driven design, better collaboration between stakeholders in the team, and live project management. So, this can really reduce the effort, the overall effort required to develop a product. We've seen cases where this can go down from weeks to possibly even hours, but certainly days. I just to now review the connector design a little bit and some of the high-level goals that we had. So, of course, the connector needs to be reliable, both electrically and mechanically speaking, not just on the first use, but on the 100th or the 1000th use. These are two parts that are going to be pushed together, and it needs to be robust mechanically and, of course, perform well electrically. The pins have to make contact correctly in order to minimize signal reflection and loss, because that would cause signal integrity problems. But the springs also need to hold the connector in place with the correct force so that it doesn't come out accidentally, but it can still be inserted and removed relatively easily by the user. So let's now take a look at the ModSim setup for this project. I have a little video here of the process. So again, ModSim unifies modeling and simulation, brings end-to-end product development process together on the platform. And it includes project, lifecycle, and change management, as well as collaboration and analytics. And again, we're going to use the connector design to demonstrate this. So first, a globally accessible dashboard with various tabs is set up to organize the process. On the left-hand side, you can see that the model can be visualized in the 3D Play app and discussed in 3D Swim on the right, so you can communicate with stakeholders. The requirements can be also defined in a requirements tab. And we have, in this case, both signal integrity and structural requirements. The signal integrity requirements include differential S parameter specifications at different frequencies. And also the TDR is an important aspect of the design. And the structural requirements, one of the main requirements is the insertion force. And we also have, elastic behavior, pin alignment, and durability in the requirements as well. Okay, so want to show now the process we use for actually building the model. We're actually using SOLIDWORKS. We're opening that from a bookmark editor, which conveniently filters the models that we're working on. So here you can see SOLIDWORKS connected. Connected means it's connected to the 3D Experience platform, and you can see the entities on the right are platform objects derived from the SOLIDWORKS model. The model actually has sub-assemblies and many parts in the different sub-assemblies. Very nice tool for handling assemblies. You can drill down into individual parts and modify those, and the assembly will update. And you can also create different configurations. We needed a configuration for electrical design where the two parts are pushed together, and another configuration which is prior to the connection, which is used for structural analysis. Here on the right-hand side, you can see, look into the platform and all the revisions, history, PLM management, and also you can view the relationship between different parts in the assembly. So when we run the electromagnetic simulation, typical outputs are, as Valdemar said earlier, we'd like to see the fields. 3D simulation can provide a view of the fields and surface currents. And here you see the signals flowing across the connector at two different frequencies, 1 gigahertz on the left and 10 gigahertz on the right. So the main aim of signal integrity analysis is to ensure that the signal can travel from one side of the connector to the other with minimal reflection, minimal loss, minimal radiation, and minimal crosstalk between different differential signals. So let's see how the simulation is done within the ModSim environment. So back into the platform, we can browse the apps that are on the platform, and one of those that we want to use for simulation is, of course, CST. We open the connector for CST, which means it's connected to the platform, and open the connector model. So you can see here that CST is now connected to 3D Experience. There is a quick start guide that is there to help new users. You can use that to help set up the model. In this case, we've defined all the different ports to receive signals. We've used a highly efficient transient TLM meshing scheme, which allows you to really localize fine cells on the detail through a cell lumping process. We set the frequency range according to the spectrum of the signals. We're using open boundary conditions here to absorb any radiated fields. And as shown before, we can also link with the schematic. And in this case, I'm using mode converters to analyze the differential signaling, and then setting up some post-processing templates to extract the TDR results as parameters. Here's the TDR. And also the IDI, which is, these are critical KPIs for signal integrity. And then finally, having run the simulation, we can save the model with the results back to the 3D Experience platform. And that allows us to then use a physics simulation app on the platform to actually display the results on the platform. Here's some of the 1D results, the TDR result, for example. So, this makes it very convenient to discuss the results with other stakeholders in a common environment on the platform. You can do this for structural, thermal, EMAG, any of the physics. And you can even see the, the electromagnetic fields. Let's say you see there's something strange with the current or something. You want to discuss that and kind of defend making a design change from a signal integrity point of view. It's a really nice way to collaborate and discuss, through this lightweight results, by the way. So, it's all shown in a browser, very convenient for discussing results and making decisions with other colleagues. So now I want to just look into the results a bit more closely. So the TDR is actually within spec. So we did quite a good job on the first iteration here. the spec was 90 ohms plus or minus 8 ohms, so between 82 and 98. But it's dipping down to just below 84 ohms, so it's a little bit close to the spec, and we thought, okay, let's try and improve that. Okay, so we also looked at the S parameters on the right, and generally speaking, they were within the specification. We have very small insertion loss, less than half a dB across the whole spectrum, and the reflection loss is below 18.5 dB. So to try and improve the TDR, and I always encourage folks to do this, is look at the fields and try to understand what's going on. And here you see an animation of the electric field. This is a time animation, by the way. So it's often you see phase animations that are performed at specific frequencies. One nice feature of time domain simulation, 3D time domain simulation, is that you can generate directly time animations like this. So you can actually see how the signal is propagating in time across the connector. And notice I've sort of drawn a circle around an area of interest here where the springs that are in the plug, as you push the connector in, they slide over the pins of the socket, and as you slide the springs over those pins, you're left with these sort of stubs, which cause capacitive coupling between the springs and the pins, and that capacitive coupling is what is causing that swing in TDR impedance. So we can actually visualize that, and again, you could drop this back onto the platform, discuss it with colleagues, and propose a design change, explain why you need to make the change. So to make the design change, we just simply go back to the SOLIDWORKS model. We can go into the assembly and edit the specific part. We can create a new revision on the platform to handle, for product lifecycle management, the versioning. So everything's sort of managed in one place. And by the way, the structural engineer will also get a notice that there's a revision. So any stakeholders will see there's a revision. We simply go in and shorten the pins in the sketch, as you saw there. And then we can save this revised version back to the 3D Experience platform. So what I did here is I created a new tab on the dashboard to show the design modification results. And then there's a really nice app called Performance Trade-off that you can just drag onto the dashboard, and you can associate KPIs with results, and it very nicely evaluates the performance and color codes, and gives a ranking and score for all the different iterations. I'm only showing two different designs here, but you could have a whole multitude of different designs, especially if you did a sort of design of experiments, and really use this performance trade-off app to easily extract, okay, which is the best performing version of the model. And we can see, that the TDR with these reduced pin lengths, we've got rid of that parasitic capacitive coupling, and the TDR has improved. So, it was before dropping below 84 ohms, and now it's staying very close to 9 ohms, in fact. Okay. So we can also confirm this, by looking at the time animation of the electric field again. So again, on the left-hand side, that's the original design with the longer socket pins, the stubs, as I call them, that was causing this drop in TDR. And you can compare that on the right-hand side is the design with the shorter socket pins. And if you look carefully, you can see that the signal is able to flow across the interface now with less discontinuity. That stuff was really having, you know, an effect on the performance of the design. So another aspect of the design from signal integrity point of view, this is an interesting aspect because discussing with my structural colleague Brian, he mentioned that we ought to add some retention springs to the design because the socket springs themselves may not be sufficient to keep the two parts held together once the plug is inserted in the socket. So we wanted to add these retention springs to keep the parts together. Of course, as soon as he mentioned that, I thought, oh, you know, that might have some impact on the signal integrity performance, especially because the retention spring was going to be metallic, and any metallic object, as I think most of us know, you know, could have a big impact on the electromagnetic fields. So it's very difficult to guess, you know, without doing simulation. Okay, would this retention spring have any influence or not? And this is really the power, you know, of using 3D simulation. It's very easy to assess these kinds of or answer these kind of questions. So here you can see on the right-hand side the TDR, the original resulting green with the long pins where we had the issue with the dip in impedance, the redesign with the short pins, and then within the red curve is when the retention springs are present, and the blue curve is when they are removed from the design. And you can see that there's barely any difference in performance. So that was good to see. So we could verify back with the team that the retention springs were not going to be an issue from signal integrity point of view. So another thing that is very important from a signal integrity point of view is crosstalk. So in this connector, we have several differential pairs for high-speed signaling, and you know, one of those pairs may be used for transmit, another one for receive, and another one for data. And we don't want the signals to couple with each other between the differential pairs, and we can take a look at the S parameters, the differential S parameters, to evaluate the near end crosstalk and the far end crosstalk, as shown on the diagram on the left. You can see that, generally speaking, across the whole spectrum from up to 10 gigahertz, the crosstalk is, well, the near end is below, let's say, 32 dB or so, far end below 37 dB or so. And what's also interesting is that shortening of the socket pins has actually improved the performance from a crosstalk point of view, as well as TDR. So that's really good to see. So in addition to you know, all this cybernetics, of course, you know, I was working with my colleague Brian, who was performing structural simulations in parallel. It was a very collaborative kind of project. And my colleague Jonathan is, unfortunately, Brian is not able to be with us today, but Jonathan is going to tell you a little bit more about the structural side of the project. So over to you, Jonathan.
Yeah, thanks, David. And yeah, of course, I do want to credit Brian for doing this work with David, but I'll be presenting it on his behalf. So let me just go ahead and share my screen. All right. So yes, I mean, as David was saying, and similar to the electronic or the electromagnetic requirements, structural requirements can be added and checked during the design and simulation phases. So in fact, we've got the same app open here. This is the requirements structure editor, and a couple of structural requirements which need to be satisfied to meet industry standards are shown here. These include things like the insertion and removal force, which should be between 8 and 20 newtons, and the durability. That's the number of insertions required for the connector, typically required to be over 10,000 insertion and removal cycles. Another design requirement is that there's no permanent deformation of the components during the insertion and removal process. And additionally, there are other requirements like the lateral force, the maximum lateral force before damage occurs to the connector, and even another one, which is the mounting force to the PCB. So you can see there's actually an awful lot of structural requirements that need to be managed for this project, which just increases the complexity, which is why this kind of process, this kind of platform-based approach, really does help to manage all of that complexity. All right, so using the identical CAD model, the same CAD model that David was using, generated from SOLIDWORKS, we can generate a finite element analysis model of the mechanical parts of the connector. That's what you're seeing here. This model begins with the connector unengaged or disconnected, if you like, so that we can determine the final deformed configuration and stress state of the connector once it's plugged in or engaged. So the modeling and simulation was performed within the 3D Experience platform using the structural apps. And these enable the structural analyst to use the finite element model of the connector and have it updated if changes are made to the CAD geometry. So in other words, if it's sort of a two-way process. If the CAD designer makes a change, the structural analyst will see that change, and vice versa. So if the structural analyst decides he needs to make a change to improve the performance, the CAD designer will get that change as well. So it's really a two-way process. And additionally, the results of any structural simulation can be reported within the 3D Experience dashboard of the project, and you can compare results to those requirements directly and use the trade-off app that David was showing earlier to compare all of the results in one view. So in fact, the connector insertion simulation we ran on the initial geometry showed that the connector shifted within the shell and relieved any stresses in the springs. However, this would result in poor electrical contact. So as a result, a modification was made to the spring angle from 8.5 to 9.25 degrees to increase the contact in the spring. So we rerun the simulation with the new pin angle. This is showing that dynamic simulation here. So the results of the second simulation showed significant contact stresses between the connector and the socket pins, and the corresponding bending stress in the connector pins. The pins remained elastic, and sufficient contact is made to ensure a good electrical connection. One point here is that the stresses on the retaining spring, that extra component that David was talking about, which can be seen moving to the right of this. Let me just play that again. You can see that retaining spring moving to the right here. The contact stress there is still very low, which is an issue we might want to deal with, because if that's too low, then the connector may fall out, the plug may fall out, which is obviously an undesirable experience. So we then perform an evaluation of both the defined and functional requirements for all of the simulations. The insertion force is in fact still well under the required minimum of 8 newtons. You can see on the left here. And we ran into a series of issues, which is part of the process here. We uncovered a number of issues, and another one is that the recess for capturing the retaining spring wasn't fitting the retaining spring very well, and that's due to the vertical shift of the connector as it's inserted. So there's a retaining hole which the retaining spring is meant to fit into, but because the connector was moving up as it slides in, that wasn't making a very good connection. So that's something else that needs to be redesigned. You can see that on the right-hand side here. So using the SOLIDWORKS interface, this is SOLIDWORKS here with the platform dialog open on the right-hand side. We can modify the retaining spring. And the first modification is to change the parameter for the spring angle. This enables more opening of the spring assembly, creating a higher force. The second modification is a section modification, creating a thickness cube stiffness increase. The SOLIDWORKS files are modified with the connected app, which is then resynced with the platform, as we've seen previously. And during that process, the structural analyst will get notified automatically that the geometry has been modified. I'll get that in a notification through the platform or through his email, and that he'll be told that he then needs to run an update of the model and remesh and rerun the simulation. So the results of a third simulation, which we're showing here, illustrate the increasing stresses in the retaining spring around the pin card into the capture recess. This shows that the retaining springs in the this shows that the stresses in the retaining springs are much higher than the stresses in the connector pins. So the connector pins only have to have enough contact force to guarantee electrical connectivity, whereas the retaining spring must supply the insertion and removal force. And in fact, you can see that in this image on the left-hand side here. You can see as the contact pin is moved into the connector, there's a certain amount of force generated, which you can see on the left of the graph here. And then as the retaining spring moves in, then that force increases significantly. And that's the retaining force that we need to keep the connector engaged. All right. So I ran through that a little bit quicker than I expected. But anyway, just to give you a quick summary of what we've shown here. So ModSim is really about connecting the end-to-end product development process, including connected physics and multi-physics simulations as well. So it unifies modeling and simulation, so taking CAD data directly through a platform rather than through something like file sharing. And it connects that CAD directly to simulation. But in addition to that, you can also manage your requirements directly through the platform. You have the ability to do project management, things like tracking project milestones and so on. And you also have the ability to communicate in a what we call our SWIM application. It's a little bit like Facebook or LinkedIn, where you can chat with a certain group and directly talk about the model and the results. So all of that's managed directly in this 3D Experience platform environment. And I think having that common data model is really the key here, because everybody's working off the same model. When you transfer files that it's very hard to maintain version control. Very difficult to do that. You number, you change the file name to include numbering and so on, but in the end, things get lost or misplaced, or somebody misunderstands an update. So having that common data model, I think, really is a key feature here to maintain synchronicity across the whole project.